What's up, kids? Charlie Abuso here, chemistry teacher. You're my chemistry students. We're going to do thermochemistry class number 3. We're going to do notes number 52 to 76. Got to have a calculator. Got to have a reference table. We're going to write on that today. We're going to write on it right now. So pause. Go get your reference table because you're going to have to draw something big on it right now. We'll do some math today. The math has some weird formulas, but the formulas are all written on the back page of the reference table. There's not a lot of numbers in these formulas. Actually, they're all numbers, but they're all letters. The letters all mean something. It could be easy to, oh, I don't know how to do this. Easy to do that. Or you can say, hey, you know what? Chemistry's hard. I'm smart. Teacher's good. It's going to work out for me. This is where the mathematics is exquisitely beautiful and will prove practical hands-on stuff. How much energy does it take to melt this particular ice cube? You're going to be able to really do some cool stuff today, but you need a calculator and you need not to get all wimpy on me, right? You're like, oh, I don't understand. Of course you don't understand. That's why I'm going to start teaching it to you. And this Zoom business, as you know, is not even as good as when you're in the room. We're going to practice a lot. Don't be a baby, right? Take a deep breath in through the nose and get psyched. All right. On the very back of the reference table, down here on the bottom, there's a lot of space. We're going to draw this water constants and formulas. Now, this is a temperature line, and this temperature line is going to show you for every temperature change or every phase change for water, what thermochemistry formulas you're going to use and what constants you're going to use. Now, on the bottom, pick 2 spots where there's plenty of room for the melting point, which is also the freezing point, and then the boiling point, which is also the condensing point. And you can write the temperatures down too, so you don't forget them. At standard pressure, the freezing and melting point for water is 0 degrees centigrade at 273 Kelvin. The normal boiling point for water, the normal condensing point, 373 Kelvin or 100 centigrade. You knew that. So far, we're just jotting some stuff down you already know. Now, there's 2 triangles. The points represent the phase changes. We're going to go from the solid on the left, liquid in the middle, gas on the right. Now, in the middle, whenever you change temperature for water from anywhere from 0 up to 100, any change in temperature, there's only one formula to use for changing temperature. And that formula is Q equals MC delta T. We're going to practice that formula today. Now, for liquid water, the C value, the specific heat capacity constant, is listed for us in table B. Liquid water takes 4.18 joules to make every gram of it change by 1 unit of temperature, Kelvin or centigrade. But look what happens on the left. You can have really cold ice and warmer ice. Ice gets to be up to 273 Kelvin frozen, but you might have ice that's at 237 Kelvin, really freaking cold, and you can warm it up to 273. If you have a temperature change, you have to use the Q equals MC delta T formula, but ice has a different specific heat capacity constant. It has a lower number. It's easier. It takes less energy to change the temperature of ice. Now, that number is not on the reference table. You have to write it down, but that's a real number. And this is a real class, and ice is real stuff. You know what ice is? Look out the window. I can see it today. Ice changes temperature just like water can, but it takes less energy to change the temperature of ice. So it's the same formula. If ice goes from really cold to a little bit warmer, delta T formula, but C is not the same because ice is not liquid water. Now, over the temperature of boiling, when H2O turns into a gas H2O is chemically identical, but physically it's got some different properties. It has also a different C value. So if you want to change the temperature of steam, you want to make steam go from, say, 100 degrees centigrade to 104 degrees centigrade because you got it in a container and you heat up the steam and the particles move even faster. The temperature of steam can go up, but it takes less energy to heat steam up, or, you know, there it is, 1.9 joules per Kelvin, joules per gram dot Kelvin. Now, the 2 triangle points, When H2O goes from the solid to the liquid or liquid to solid, melts or freezes, we have no temperature change. It happens at the freezing point or at the melting point. So we have the formula, what we call the cold phase change formula. For water, we use Q equals mH of F, and H of F stands for heat of fusion. Now, the heat of fusion constant is also on table B. Now, we use that in either direction, whether we're adding heat to melt it or we're removing heat to freeze it. Doesn't matter which way we go, it's the same formula. On the hot phase change side, when water boils into a gas or if the gas condenses into steam, we use a slightly different formula because we have to use what's called the heat of vaporization constant. And the heat of vaporization constant for H2O is 2260 joules per gram. Now, what's really cool, and you can remember this too, this setup is good for every single substance as far as the formulas go, but all substances have different specific heat capacity constant. We're going to do a problem in a little while about melting gold. Melting gold, right, has a different heat of fusion than water does. It's not going to be 334 joules per gram. Every substance has different constants, but they all use the same formulas. All stuff works the same, but there are different constants. Just like everything has a different melting point, they also have different heat of fusion. They also have a different heat of vaporization constant. They also have a different specific heat capacity constant at all three phases. We'll practice this. This is a little scary. Let's get it out of the way in the front, and now it's going to be easy for us. Okay. How many joules of energy required to freeze 355 mLs of water? I picked that number, I'm pretty sure, because in a can of seltzer, there's 355 mLs, and there are. So say you take a can of seltzer and you put it in the freezer. If it's really cold, if it's 273 Kelvin, 0 centigrade, really cold, but liquid, and you put it in the freezer, how much energy does it take you have to remove to make it all solid? Now, this is no change in temperature. This is going to be the Q equals mH of F formula. This is a cold phase change. And it might be fun to point out that 1 ml of water is equal to 1 gram because the density of water is 1 gram per 1 ml. So we can just switch 355 mLs into 355 grams. It's really easy. Now, the formula says Q, the amount of heat in joules, is equal to the mass times the constant called the heat of fusion. We just decided the mass is 355 grams and the heat of fusion constant is right here in table B. So let's plug those numbers in. Look what we got. I'm getting my calculator. Get your calculator. 355 times 334 equals, and let's see if I can get that number. See it? 118,570. Look what I'm doing. Oh, we got to cancel the grams. And then look, 118,570 rounded to 3 significant figures. In order to freeze this much water at the freezing point, it's 273 liquid. We want to make it 273 solid. We have to remove 119,000 joules. That's just an amount of energy. We can do this. That's what your freezer does. It pulls that much energy out and turns your liquid water into ice cubes. Now, what about this one? That's a pretty big meatball size snowball. Say you get your gloves together, make yourself a snowball, you run up behind one of your best friends, you pull the back of their coat out and throw the snowball back down their coat, and it gets on their skin. The body temperature is going to melt that pretty quick. How much energy does it take for your body to melt 415 grams of snow from solid to liquid? This is going to be a cold phase change formula, so we're going to use the same formula. Q is the amount of energy in joules. M is mass. H of F is a constant for H2O, and that's in table B, 334 joules per gram. Every gram is going to require 334 joules in order to melt with no temperature change. So we plug in the numbers. 415, I'm going to do this on my calculator. 415 times 334. And look at the number I get. Where is that? 138,610. What do I get? 138,610. We round it to 3 significant figures. 139 joules, 139,000 joules. This is not hard. A snowball goes down your back. You can understand that. How much energy does it take to melt? Well, it's a weird unit, named after some guy with a big beard and a mustache. But that's how much energy. That's the numbers we use. This formula is easy. The energy equals the mass times a constant. The mass is in the problem. The constant's on table B. It's a multiplication problem. This is not hard. We can do this all day long. You can freeze it or melt it with the same formula. It's called cold phase change. All right. This is a different problem. Look, there's a campfire. Maybe Thomas Buckholz is putting a can of pork and beans that he didn't open in that fire. All right, how many joules does it take to warm up 375 grams of water by 7.5 Kelvin? Now, this is a different problem. This is going to have a change in temperature. Change in temperature. It's liquid water, and we're heating it up by a certain temperature, by a certain number of Kelvin, 7.5 Kelvin. To do this problem, we have to use a different formula. This is not phase change. We're warming up water. It's going from cold water to hot water. It doesn't matter hot or cold, cold or hot, but in this case, it's colder water that's being heated by the fire and getting hotter. There's a change in temperature. So we have to use this formula. Q equals MC delta T. Q is still the energy in joules. M is still the mass. C is a different constant. And the specific heat capacity constant for liquid water is 4.18 joules per gram dot Kelvin. Now the delta T, that means the change in temperature. This one's pretty easy. We got it. The change in temperature is 7.50 Kelvin. We don't have to figure it out. We don't have a starting and ending temperature to subtract. There it is, it's 7.5. So let's plug the numbers in. 375 grams times 4.18 joules per gram dot Kelvin times 7.5 Kelvin. Now, the black slashes, the grams in the numerator cancel the grams in the denominator. The Kelvin in the numerator cancel the Kelvin in the denominator. And the units that are left over are called joules. Now, we're going to do this math. Get your calculator. 375 times 4.18 times 7.50. Now, listen, I'm doing this math. You do this math. I'm not doing this for me. I'm doing this for you. Look at that number. 11756.29. Let's see if I got that. Look at that. 11756.2. Oh, I don't know, 0.29 or 25, whatever that was. But it's going to round to three significant figures. How much energy does it take to warm up 375? That's more than a seltzer can. This is 355. So a little bit more than a seltzer can. You want to warm it up by 7.5 degrees. That's how much energy it takes. Do you care? No, this is a stupid math problem, but it's knowable. This is not magic. This is not fantastic. This is not impossible. This is a formula on the reference table. There was almost no thinking. It's a delta T problem. You have to insert the delta T. You have to use this formula. All right, I thought somebody was coming in. Have fun. Oh, look, there's a shiny band of gold. I love shiny bands of gold. There's a great song by Neil Young called Band of Gold. Keep me searching and I'm growing old. It's a great song. You should really listen to that song today. Neil Young, Band of Gold. No, I'm crazy. Heart of Gold. Band of Gold is also a good song, but that's by a woman. I can't remember her name right now. Neil Young, keep me searching and I'm growing old. What's the specific heat capacity constant for gold? If it takes a certain number of joules to warm a ring up with that mass from this temperature to that temperature, right? You're gonna take it at room temperature, you're gonna heat it up to 355.5, be too hot to put on. What the heck is this question even asking? This question says if you have a ring that's 34.2 grams at room temperature, like body temperature, and you heat it up to 355.5 Kelvin, how much, if it only takes 271 joules to do that, what is that C value? What is that constant? There's a delta T problem. This is definitely a change in temperature. There's only one formula. So let's write this formula down. Now, the Q. Q is the heat in joules. That's where the 271 joules goes. What's the mass? 34.2 grams. What's the C? That's the question. What is the specific heat capacity constant? And what's the delta T? We're going to do a simple subtraction to get that. This is the setup. Where did the 61.5 come from? I think I have it on the next slide. No, I don't. Let's see what we got. The 355.5, this is the starting temperature, the ending temperature, minus 294.0 equals 61.5. That's the change in temperature. Now, in order to get C by itself, we have to divide 34.2 grams times 61.5 Kelvin on both sides. So I get the C by itself, and now I have the joules divided by the grams in the Kelvin. Now this takes a little bit of calculation, right? You're gonna have to do the math nice and slow, but look at the units. The joules in the numerator divided by grams times Kelvin, and that's always the unit. Now, what does this mean? What is this 0.129? That means, for instance, if you want to change the temperature of liquid water, you have to add 4.18 joules to make every gram change by 1 Kelvin. But for gold, you don't have to add 4.18 joules. You only have to add 0.129 joules. This is a very little amount of energy. Metals heat up really fast. They have very low specific heat capacity constants. You know that, right? You know that. If you have if you have an aluminum chaise lounge in your backyard near the pool, and you're having a nice hot day, and you're drinking a nice cold seltzer, and you're enjoying yourself in the sun, you get so hot, you're like, you know what, I got to go in the pool now. And you put your half a can of seltzer down, and you go in the pool for 20 minutes, and you come back out, and you take a quick sip of seltzer, like, ugh, it got warm. But if you sit funny on that aluminum chaise lounge and don't get just the seat, but you hit some of the metal, that metal's going to burn you. It's going to burn you. Your skin is going to get hurt. You know why? Because the aluminum, which is a metal, has a low specific heat capacity constant. And when the sun's energy is coming down and hitting the earth, it's going to warm up your can of seltzer, but not so much because it takes more units of energy to warm up seltzer. It warms up slower, but the metal of the chair is going to heat up quick. Metals have really low specific heat capacity constants. Every substance has its own, and we can solve for this. We can solve for any one of these variables. I love Thermochem. I hope you're loving this. All right, what is the specific heat capacity constant of copper? Copper is what the old pennies are made of. If you can put a certain amount of energy to warm up a certain amount of grams, and from this temperature to that temperature, what's the C value? I fully appreciate you don't want to do this problem. But this is math. This is chem. This is you. Delta T, we write the formula down. There's only one formula in heat for a change in temperature, and that's the formula. Q equals MC delta T. In this case, we know what the Q is. It's 951 joules. We know what the mass is. It's 41.63 grams. The C value is the unknown. What is the specific heat capacity constant for copper? And the delta T, well, we got to figure out what the delta T is. 951 joules equals 41.63 grams times the unknown C times, and look at the bottom right. How do you figure out the delta T? The final temperature, take away the starting temperature, the difference is going to be the change in temperature. Now, in order to get, in this big problem on the left, in order to get the C value by itself, we're going to divide both sides of this equation by the grams times the Kelvin. And then look what it turns into. The C value by itself is going to equal the 951 joules divided by 41.63 grams times 58.4 Kelvin. Watch the units. The joules is in the numerator divided by grams times Kelvin. This is always the funky unit for specific heat capacity constant, and the number comes out to be 0.391. Now, this number is higher than gold, which means if we put a piece of gold and a piece of copper on a hot plate and heated it up together, the copper will get hotter slower. The gold will get hotter faster. It takes less energy for copper to change temperature. It takes more energy, not much, but more energy to make the copper get hotter. Watch the units. Those are the special units for specific heat capacity constant. Now, this is an unknown What is the heat of fusion constant for an unknown? This time, we're trying to find out what the heat of fusion constant is. So for heat of fusion, we have only one formula. Let's write that formula and plug stuff in. We're going to look for the heat of fusion. In this case, we know the number of joules. That's Q. Q is equal to 6750 joules. Q is equal to the mass, 28 grams, times the unknown. So plug in this stuff. Look what it looks like. We're going to solve for the heat of fusion. We know the joules, we know the mass, we're going to solve for the heat of fusion. To get heat of fusion by itself, we divide both sides by 28.0 grams, and the heat of fusion is going to equal to 6750 joules divided by 28 grams. Do the math, 241, and the unit is very important, joules in the numerator divided by grams in the denominator. 241 joules per gram. That means in order to melt this stuff, you'd have to insert 241 joules for every gram to melt it. I love this stuff. All right, this is a cool problem, and it's a cool logo, right? You know, Sub-Zeros are really nice freezers. They're very expensive. They work nice. It's just a cool logo. Here we go. I don't have one. I kind of wish I did, but it doesn't matter. Mine works pretty well too. How many grams of water can be frozen when you remove this many joules from it? Now, this is a backwards question. You know, some of these are wordy and you want to try to figure out what they mean. In this case, you know the Q, and it's freezing, so it's a heat of fusion problem, and it's water, so you know what the constant really is. In this case, we're going to solve for the number of grams. Any one of the things can be a variable, any one, Q, M, C, delta T, or Q, M, and the heat of fusion or heat of vaporization. Any one of those. We're going to this time solve for grams. So let's write the formula. Q equals MH of F, right? Heat of fusion. We know the Q, it's given, 87,500 joules. And we know, since it's water, that the heat of fusion constant is in table B. And so we're going to plug in the numbers. 87,500 joules is going to equal unknown mass times the heat of fusion constant for water, 334 joules per gram. To get mass alone, we're going to divide both sides by 334 joules per gram. And watch what happens to the units. On the bottom left, we have joules in the numerator, we have joules in the denominator, and they're going to cancel. Now watch the unit now. The grams is actually in the denominator of the denominator, and mathematically that makes it pop out into the numerator. So when we do the division, we then bring that grams out of the denominator back to the numerator. It's a little mathematical, I don't want to call it sleight of hand, but that's how it works. And then you round for three significant figures. So how much water? So you put a whole bunch of water into the Sub-Zero freezer. You remove exactly 87,500 joules. How much of that water has frozen? 262 grams. It's a snowball. 92.0 grams of a substance will absorb this wacko number of joules. The temperature increases. What is the specific heat capacity constant for this unknown? Well, there's only three formulas, and this one has the delta T in it. So which formula are we going to use? We're going to use the one with the delta T. Have to have a delta T. Q equals MC delta T. What's the Q? Q is the joules. What's the mass? 92.0 grams. What's the C? That's the unknown. What's the delta T? You got to do a little subtraction. Watch what we got. 27,496 joules equals 92 grams times C, which is the unknown. And on the right, the end temperature minus the starting temperature in centigrade. Now, this is important. The change in temperature in centigrade equals the change in temperature in Kelvin. Not the same temperature, but the same amount of change. So we can just do the delta T really quick. Just subtract the temperatures. The difference in temperature is the difference in temperature in both units, Kelvin or centigrade. Now, in order to solve for C, we have to divide both sides by 92 grams and 71.5 Kelvin. So look what I did. I did it on the right and I crossed everything out, but on the left, I have all those joules divided by 92.0 grams times 71.5 Kelvin. Most important, watch the units, joules per gram dot Kelvin. And lo and behold, the answer comes out to be 4.18. Where have we seen that number before? Who remembers? Here's that number, 4.18. That has the specific heat capacity constant for liquid water. It's probably water, H2O. Maybe it's water if you're from Vestal, but I think it's water, probably. All right, we're nearly done, right? We're nearly done, but this is a big problem. Look at this problem, holy smokes. You put 155 gram snowball. This is not too big. This is actually a small meatball. At -4 centigrade. So this is a little colder. This is below the freezing point, down the back of your friend's jacket. It ultimately warms up to his body temperature, 37.00. How much energy did this take? Now, this is tricky. We have to go really slow, but it should be obvious. The snowball is below freezing. It's frozen at -4. What temperature does it melt? It melts at 0. Can't melt yet. When you throw it down his back, it can't melt. First, you have to warm it up. First, you have to warm it up to the melting point. That's the first amount of energy. So the first step is a delta T problem below the freezing point. Now, when I start it like this, it's 155 grams, Q equals MC delta T. Ice has a different specific heat capacity constant. See that little asterisk where it says warming ice? That means, hey, pay attention. It's not liquid water, so it's not 4.18. It's actually 2.10. You couldn't possibly know that, but I gave that to you in the first slide and told you to pay attention. It was coming. Here it is. Now, what is the change in temperature? It goes from -4 up to 0, to 4 degrees centigrade or 4 Kelvin, and we'll keep the significant figures. So the first step, you throw the ice cube down there. I guess that's the first step. The next step, let's warm up the ice, right? Because that's the first thing that's going to happen. It's going to take 1,302 joules. Now, I know the significant figures are bad, but we're going to add this all up and take care of significant figures at the end. First, we're going to warm the ice up. Then, we're going to melt the ice. Melting the ice requires Q equals MH of F. So what do we got? We still have 155 grams, but now we're phase changing it. We're going to put in 334 joules per gram. And so the second step requires a lot more energy. To warm up the ice, kind of an easy thing to do. To melt the ice takes a fair amount of energy. That's why your friend feels so cold. Now the water is liquid at the freezing point. It's actually 0 centigrade. We got to bump it up to body temperature at 37.0. So to warm the water up to complete liquid at body temperature, we still have 155 grams. We're going to multiply that by 4.18 joules per gram per Kelvin. That's how much energy it takes to make every gram of water change by 1 Kelvin or 1 centigrade. And the delta T, we had to do it in Kelvin, but the delta T is 37 degrees centigrade, so the delta T is 37.0 Kelvin. And it takes another almost 24,000 joules to warm it up. So first we warmed the ice, then we melted the ice, and then we warmed up the water. And then we have to sum this all up. We have to sum it all up. So it comes out to 76,774, which rounds to 3 significant figures. In real life, thermochemistry, it's not limited to one little step usually. I mean, you could take some water and you could heat it up on the stove, or you could put some water in the refrigerator and make it colder. You could just do one formula. But the ice outside, it's not at the freezing point. It's probably below. First, you have to warm it up before it'll melt. It won't melt till it gets to the melting point. I know it doesn't seem like that to real normal people because you can't tell the difference with your hand or your back, -4 or 0. It just feels freaking cold. But it won't melt until you warm it up to the melting point, and that takes energy. And then when you melt it, that takes energy. And then once it's liquid and you warm the liquid water up to body temperature, it takes more energy. This is like going out to a fancy restaurant. The red step is your appetizer. The blue step is your main course. And the green step is your dessert. The waiter is not going to bring you 3 checks. They add it all up and give you 1 check. You pay 1 price. Tip 20% if you're a nice person. You add them up. This part plus that part plus that part is the total amount of energy required to do a problem like this. Each part is easy, and then you sum them up. In addition, you learned in the 3rd grade. I think this is the last problem. Look at that cool picture. That's a really, really steamed up window, and somebody drew a little heart in there. See? Heart. Hearts are for love. Okay. 5.75 grams of steam condense onto a piece of glass. It's hot. Then it's going to cool down. So how much energy is emitted by this? Well, first we're going to condense it from the boiling point from gas to liquid. Then we're going to make the liquid at 100 centigrade cool down to pretty chilly, 23.5. So the first step is called condensing. Q equals mH of E, the hot phase change. Q is going to equal the mass times the heat of vaporization constant. That's for H2O, that's 2260 joules per gram. The grams cancel, it's going to release that much energy just to condense. Now, it's still at the boiling point. Well, now it's condensed into liquid, but it's still at 100 degrees centigrade. To bring it down to 23.5 degrees centigrade to cool the liquid with a temperature change, we have to use Q equals MC delta T. Now, the Q is the joules. We're going to work that out. The mass is still 5.75 grams. The middle, 4.18 joules per gram dot Kelvin. I took the dot out of there because I couldn't fit it, I think. I don't think I could fit it in this, but it really is dot Kelvin. And the delta T is the difference between 100 and 23.5, which is 76.5. So in order to cool it, it releases an additional 1839 joules. We sum it up and we round the significant figures at the end. So 5.75 grams of steam condenses and then cools down on a cool day to 23.5 centigrade. It releases some energy to condense and it releases more energy to cool down, and you sum up the 2 parts. This is a less fancy restaurant. This is like going to Charlie's Bagels when I used to have it. You have a bagel sandwich and a cookie, right? I give you 1 bill. Pay for all of it at once. Round up. Table I. All right, we're nearly done with this stuff, but we're going to go look at table I. Table I. Table I is a title. It's called Heats of Reaction at 101.3 kPa and 298. What the heck does this mean? Well, this is going to tell us about the thermochemistry and something called heat of reaction. It's a constant, and it's going to happen at normal pressure and room temperature. It's not at standard temperature and pressure. This is standard pressure, but room temperature. Not 273, this is 298. This is normal room temperature. Now, on this, there's 25 chemical reactions and also a whole bunch of physical changes. Now let's look. From the top down to here are chemical reactions, but starting with KNO3, the rest of the way, that's just when solid salts go into water and become aqueous. Sometimes when you put salts in water, they either release heat or they absorb heat. So there's going to be a heat of reaction. But really, the top one's a heat of reaction. Starting with the KNO3, they're actually called heats of solution. It's a little different, but it's the same. It's thermochemistry, but it's not really chemical reaction. They're not all chemical reactions. The state likes to play with your mind like that. Now, they all have something called delta H. Change in heat. Delta H is the heat of reaction. It basically means how much energy is released or how much energy is absorbed when this balanced reaction or this balanced phase change occurs. Delta H, and they're positive or negative. The change in energy or the change in heat. How exothermic, how endothermic, and the unit here is not joules, it's called kilojoules. Just another step of mathematics, nothing a big deal. Now, if you take a walk, a really short walk, you could walk 1 meter, one big step. But if you want to walk a kilometer, That's going to take you 5 minutes. It's 1,000 meters. Kilos are bigger. A gram is really small, like a pencil eraser. A kilogram is like a baseball. You can knock somebody down with a kilogram or something. Kilojoules is 1,000 joules. Kilo means 1,000 times. Don't worry about it. It's just a number. It's a number. Now, some of the delta H are negative, like the very first one on table I. What does the little asterisk mean at the top of the table? See this little asterisk right over here? You got to go all the way down here to see what it means. Ooh, I can't even show you. Right down here. It says a minus sign indicates exothermic. A minus sign indicates exothermic. That means if the delta H is a negative number, that heat was given off. That also means that if the delta H is a positive number, that energy would be absorbed. Now, one of the trickiest things we're going to have in this whole class is a negative or positive delta H. If you have money, how much money do you have? You don't have positive money. If you don't have money, if you owe me $5, you don't have negative money. If you ever opened your wallet when you owed me $5, there would not be a minus $5 bill in there. There's no such thing as negative money or positive money, right? If you eat food, you will gain weight, or if you don't eat food, you might lose weight. But you don't eat anything that has negative weight. There's no such thing as negative weight or positive weight. There just is. Energy is. It's either absorbed or given off. The positive and negative, we're going to see in the next section of chem, is because of a graph. Is the energy going up or down? Is the energy being emitted? Do the products have less energy than they started with, or they have more energy than they started with? Did they absorb energy or lose energy? The positive and negative here just are indications of whether or not the energy is emitted or absorbed. It's not positive energy, and it's certainly not negative energy. There's no such thing as negative energy or positive energy. Energy cannot be positive or negative. It's like money, right? It's either positive or negative. A negative just means exothermic. Now, we didn't do the demo because the slideshow is too long, and I'm going to actually do it in class, and I'll make a separate little slideshow for this particular endothermic reaction, but I couldn't take this out of the slideshow. The demo was very endothermic, and you'll see that soon. And if it was an endothermic reaction that you saw, the delta H would have to be positive, right? And that means if the energy had been emitted, it would be negative. But our demo that you didn't see yet, you will see, was going to have a positive delta H, right? Positive. Now, this is the last problem we're going to do. We need to look at the first reaction right at the top of the table. And you're pretty familiar with this. This is combustion. It is combustion. It's when methane and oxygen combust into carbon dioxide and water, and they give off a lot of heat. How much heat? We're going to get to that. How much heat? We're going to figure out right now. So these reactions are always exothermic. That's why the delta H is negative. What is kJ? Kilojoules. It's a unit of energy. It's much bigger than joules. So what this chemical reaction says, when 1 mole of methane and 2 moles of oxygen make 1 mole of carbon dioxide and 2 moles of water, it releases 890.4 kilojoules. 1 mole of methane will release that much energy. It's perfect mathematical, perfect. 1 kilojoule equals 1,000 joules. 1,000 grams is a kilogram, 1,000 meters is a kilometer. Kilo just means 1,000. Don't let it get you all anxious. Hey, we're done. We're done, all right? I love Thermochem. I'm going to make that demo in a few minutes. You'll be able to see it soon of this really cool reaction. I'm going to do it in class as well. If you come in, you will actually be able to see it and touch it. Thanks for listening. Bye-bye. How do I get out of here now? Goodbye.